I actually just came back from Locarno where I'm teaching future high school teachers in informatics. And here is a common setting. I'm asking some of them, well, you are teaching programming, let's say to high school. Which exercises do you use in your course? And here's a selection of the answers I got. Well, some of them, there is a kind of classic. I want to compute the GCD between two numbers. That's very good classic, always works. Then you have some teachers who are a little bit more math inclined, and they say, well, let's compute like the Fibonacci sequence, or let's compute factorial. That always works, especially if they are more into kind of recursion, computational complexity, speaking of competitive programming. Or if the teacher is really a hardcore math teacher, sometimes the answer is like, well, I want to do some primality testing, check whether a number is prime or not, or maybe even like using the Newton's method to compute a square root. This is kind of some of the answers I got out in the wild. Now, who knows this book? At least one person in the audience. It's a pretty famous and actually good book. You're disappointed that only one person raised the hand. It's actually a pretty good book. It has been used at least at MIT among several other institutions, and it's actually quite foundational. Now, I'm bringing this up with respect to these answers because these are all actually exercises taken from the very first chapter of this book. This is chapter 1.1, and all of the other ones are from chapter 1.2. Now, one could say, well, that's a book targeted at MIT students. That's a very selected crowd. But if you try to do this in your classroom, this is kind of the reaction you might get. Now, to classify these exercises, I've prepared a little bit like a plot in kind of business school 101 style. On one axis, we are plotting like how conceptually deep is a certain exercise. Is it exercising the right concepts we want to address? And on the other axis, I'm trying to address how attractive this is to the majority of the, let's say, high school population. And I guess we can probably agree that many of these exercises fit into this quadrant. Like they seem to be somewhat conceptually deep, but not super attractive, except for the ones who are already into math. So we need to come up with something better. Now, especially when we have to do some creative work nowadays, the answer to this is, well, let's use ChatGPT, of course, suggest some simple programming exercises. The first one is the good old classic FizzBuzz, kind of to print certain strings depending on a certain condition based on a number. Then it suggests like factorial. Here we are again. Then palindrome testing. Well, that's also a very good classic. Then we have prime numbers again, and Fibonacci. So that was not really creative, but we got at least palindrome and FizzBuzz as extras. Now, if you really go to high school teachers and say, well, I can't do any of this with my students, I need to start even from something more basic, they might say, well, I want to test, let's say, whether a number is even or odd, this kind of very simple exercises. And then what happens with the students is that they look a little bit more like this. They just get bored. And it's not even the case that necessarily even or odd is a trivial exercise. I mean, this is kind of one of the many possible solutions written in Python, which is kind of the de facto standard for teaching high schools nowadays. Well, there are actually a number of programming languages concepts that are involved in this simple program. Well, for one, we have some string literals, we have variables, we have assignment, we have calls to functions, we have to understand arguments, there is some sort of casting, typing here, we have nested function calls, and then we have string concatenation down there, then we have number literals, we have arithmetic operators, we have some arguments that are non-atomic, we have Boolean expressions, we have the concept of equality, we have a conditional if else, which in Python also requires indentation, and then we have some output, and the worst of this is that, and we have the input, which of course is also blocking. And the worst part is that the algorithm here is mixed with the IO. So it's not even, I mean, the algorithm is really trivial in this case. It's just basically figuring out how to use the modulo, the remainder operator, to check whether a number is even or odd. And yeah, this I mean, it seems very trivial, but there are actually a number of programming languages concepts that are involved. And so now we have the students that are bored and the exercises that seem trivial, which are actually not so much. And what happens in many cases is that teachers resort to games. They say, well, I have some Scratch projects and I want to, they refer to whatever game that the students here, they very like this kind of exercises, but they often spend just time decorating, changing the color of the sprite, and they move the sprite a little bit around. They don't really learn much about programming because they focus on the inessential. And here is where I would put on our favorite plot here, the Scratch projects or many Scratch projects and many games. Now, of course, after all of this, you would probably like me to deliver something that stands up to the very top right of this chart. I actually don't know what stands there, but we can try at least to figure out whether there is something here. And the idea of the graphics is actually not a bad one. Let's say that we would like to create a program that creates, let's say, a silly graphic like this small house here. We can do this in a number of ways. Probably the easiest and more common one is to use some kind of coordinate system. We can imagine this graphic living in a coordinate system. And then we can use, let's say, again, Python with a popular library to do graphics, Pillow. Can draw a polygon there for the red triangle. And then you can draw the square for the roof, for the floor, sorry, with the yellow color. And then you get this house. Now, the problem with this code is that, I mean, it works perfectly fine. It draws the house. There is some kind of dependence there between the two things we are trying to draw, namely the roof and the floor. And that dependence is really expressed with the fact that the origin of the square depends on the height of the triangle. There is that 10 there in bold, and we need to know how tall is the triangle in order to compute where to put the square. Now, this problem has been recognized already several years ago, especially in education and teaching, and I bet that many of you have at least heard of the idea of turtle graphics. Now, turtle graphics come and dates back from Logo, and there's this kind of how a square procedure might work in, might look like in Logo. You move forward 100 steps, and then you turn right 90. The idea is that you're a turtle moving on a sort of space, and then you do the same, forward 100, and then right 90, forward 100, right 90, forward 100, and then you finally have drawn the floor. Now, as computer scientists, we are offended with the last solution because there is so much code duplication. I mean, in this case, we have just the four sides, and we would like to have a construct to address this, and that's the repeat construct. That's certainly available in Logo. Now, can you spot a difference between the two implementations that are supposed to be equivalent? There is a problem here. That is the second code draws exactly the same graphic, but the position of the turtle, and specifically here the heading of the turtle, is left in a different place. In this case, in a different orientation, and that affects the code. Let's say that if we were now to write a procedure that draws a triangle for the roof, we would need to take this into account. We can't just ignore how the square has been drawn. And the point here is that the state of the turtle, meaning its position and its heading, breaks the independence between these two subproblems that we would really like to keep independent, building the roof and building the floor. Now, when I brought this up in the abstract, when kids play with Lego pieces, they actually do something pretty interesting, which is they take a seemingly boring heap of bricks, and with using very, very simple rules, they build up very complex constructions. This idea is very, very deep. Here is a quote. The acts of the mind wherein it exerts its power over simple ideas are chiefly these three, and I'm just showing the first one, combining several simple ideas into one compound one, and thus all complex ideas are made. Now, you may think that this comes from a computer scientist. We could now do the game of guessing who said this, but this actually comes not from a computer scientist, but from John Locke, a philosopher, in 1689 on his essay concerning human understanding. And so we would really like to have this in programming, to use simple ideas and building those simple ideas into compound ones to build complex ideas. If some of you maybe some of you have even taken our Programming Fundamentals 1 course. You might have seen a different way to build graphics, which is called a compositional way. This is code taken straight from Racket, and this is building the same house as before. It's creating a triangle, it's creating a square, and then it's putting the roof on top of the floor. This is all good and fine. The problem is this library, this graphics library that is included in Racket, is also used to do physics simulation, especially like for, again, building games. And so it has, again, several functions that have to do with coordinates. Like here, you want to place this rocket at coordinates 50 and 23 on some kind of background scene. And so when students discover this, that they can use, again, their favorite coordinates, they tend to use coordinates everywhere, even when they could build the graphics compositionally. And so this is what happens, that they discover that, oh, there is this function, I don't know, overlay XY, which allows me to set a displacement in terms of XY coordinates. And so here's how I can build my my graphic, again, not thinking about the combinators. I just put the roof on top, the floor. I move it like 10 pixels below or 10 units below. And that's what happens when they do this. They see, well, I mean, that's not really what I wanted. And then what they start doing is, well, maybe it's not really 10 what I had to put there. They start to do 9. And then there is still a little gap. And then they try to do, well, it's going to be 8. And then they say, well, but yeah, you see, the thing went a little bit too over. And then maybe after a while, they realize, no, they really need to compute formula the height of the equilateral triangle. And if they manage to do that, they can get the graphics right. But we're back at the same problem as before. We're again thinking in terms of coordinates. And that's not really what we would like to do as computer scientists. When we have a problem in general, we would like to decompose this problem into several sub-problems. And here's the key. We would like to be able to solve each of these sub-problems independently. So we would like to be able to come up with a sub-solution for the first sub-problem, sub-solution for the second sub-problem, and so on. And then these sub-solutions need to be able to be created independently and only later on to be composed in a general solution. And the domain of graphic is particularly interesting to do this. We can do decomposition, not in this abstract way, which is often what happens in real programs, but we can try to teach it visually. For example, here's the Swiss railway clock, and we can clearly see some distinct parts here. We have some external crown, then we have the ticks for the minutes, we have the ticks for the hours, we have 2 hands, one for the hour and one for the minutes, and then we have the special one for the seconds. And this idea of building graphics in this way compositionally, it's very old, actually. It dates back to this functional geometry paper by Anderson, and this is 1982, and has been reified to the extreme in a Haskell diagram library, which is particularly amazing and flexible. It's called diagrams. But already by looking at the signature of one of the functions to put several graphics one beside the other, you can see that Well, you have certainly flexibility and power with this library, but you definitely don't have simplicity. And in general, it's really, really hard to keep all the three together at the same time. And so we set out to give up some flexibility and some power, but to retain simplicity in create a library, again, for Python, especially given our target in teaching for high schools, that allows us to compose graphics in an immutable way with a scene graph. And we basically just start from several simple primitives, such as rectangles, triangles, ellipses, circular sectors, text. And then we have some operators to combine those. Some of them are really taken like from HTTP. And so you have overlay. You could overlay like a white cross on top of a red field. You could place one rectangle above one other rectangle, or you could place two graphics, one beside the other. And here is how a solution, let's say, for building the Swiss flag would look like with this library. We would do some imports from the library, and then we would create a red background. Then we would create an horizontal arm with the right proportions in white. The vertical arm, we could just take the horizontal one and rotate it by 90 degrees. And then we have our cross, which is obtained by overlaying the two arms. And finally, the flag, which is again obtained by overlaying the cross and the red background. Now, this is a particularly simple example. Finally, we can show the graphic. But from this, you can see that the library has been carefully designed, even though it's operating in a language potentially with a lot of complexity, like Python. It has been explicitly designed to minimize the number of required language features. And here you have some imports for functions and values from the library. You have normal function calls. You have some arguments. You have variables. If you like to use variables. You have some number literals. You have assignments. And you have a cleanly separated output that is really distinct from the algorithm. With this model, you can actually build an algebra of graphics. Once you uncover the fact that every graphic has a pinhole, has a sort of local origin, and you can, with an operator, take a graphic and repin it to another position. So you could say, well, I have this yellow rectangle and I want to pin it to the top center. Then I have this blue rectangle, I'm pinning it to the bottom center, and then I'm composing these two pinned values, and I'm composing them exactly on their pin. And this is actually the desugaring of the above function. So we have a set of elements, let's say with a type graphic that includes a pinhole, and we can prove that some of the functions, meaning this general compose, there's the one and only operator you need, it has certain algebraic properties. For example, compose is associative, meaning you have to overlay these three rectangles, these three squares, and you can do it this way, which is really similar to what we are doing in math in this way, or you could do it the other way. And when you have a type and a binary operation that is associative, well, you got a semigroup. We have also a special distinct graphic, empty graphic, that is the identity for this operation, meaning that you can compose it from the left or from the right. The operation is not commutative, but you can compose it from the left or from the right, and you still get the same graphic unaltered. And this is really similar to what you are doing in math, when you're doing, let's say, 0 plus a certain number, except the fact that addition between natural numbers is also commutative. And when you have now a semigroup, and then you're adding also an identity element, you got what's called a monoid. Now you might say, well, I don't care about all this abstract algebra. These are just fancy names you're throwing around. That's not really true. You probably care about this, because when you have this, you can actually write some nice computational patterns. For example, let's say that you have, you need to have, and that occurs actually very often, you have a need to put several graphics one beside the other, and you could write, and you could actually have your students to write a function like this beside many, which could be implemented, for example, with a loop. You start from the empty graphic. You don't need a special case if the list is empty or if the list has one element, and you can nicely put several graphics one beside the other. Of course, you don't need necessarily to use loops. You could also build this using recursion, or even more, you could use some kind of reduce or fold, given that you have your identity in your binary operation. Finally, rotate, we have other properties, such as that rotate distributes over compose. So for example, you could first rotate and then compose these two graphics, and this would be the equivalent Python code, or you could first compose and then rotate these two graphics. And when you have this operation that takes a graphic and returns a graphic and leaves all the monoidal properties unaltered, you get what's called an homomorphism, which is actually pretty cool. And it obeys to the two homomorphic laws. So here is really our idea. It's the idea of building a small library with a small set of functions that enables you to create several graphics all in this compositional way. And the idea is that you can get inspired by the graphic and the fact that you see a certain kind of, or you can try to see a certain kind of decomposition of this graphic. And that's probably easier, or at least that's our hypothesis, than actually just seeing these in the abstract. That's what happens with many programming problems later on in the curriculum. We're actually trying to spread this a little bit on high schools. We have our web platform. It's currently in beta, but you can already try and check it out. It's hosted under the SI domain. There are already some learning activities, including the ones that I've showed you, and you can already play with the library directly in the browser. And finally, as a very concluding note, we're thinking about creating Summer Academy, if you want a fancy name, for this summer, to try to bring some Swiss high school teachers and students here at USI and get them excited about the library and try to teach them some cool concepts in a playful way. That's it for my talk.